Okay, this is a quick video about complex pulley systems, and really it's just an excuse to talk about coordinate systems and constraints. So hopefully before watching this video, you've seen this before. It's called an Atwood machine, and the goal of this video is to take you from being comfortable with doing this to comfortable with doing something like this. And at the very end, I will do a double Atwood. I'll go through the whole problem because this is considered to be a difficult problem. I'll show you it's really not a big deal. It's a lot of algebra, but physics-wise, it's nothing. Okay, so this is our most basic setup. You start with a fixed pulley. The pulley cannot move. And what you've probably done with this in the past is you said, okay, one block moves up, the other block moves down. And since the length of the rope is fixed, it can't stretch, the blocks are attached, you make a statement like this: delta x1 equals delta x2. The only thing about this, though, is that one block is moving up and the other block is moving down. So these kinds of statements are problematic without coordinate systems. So we got to say absolute value. Now I'm comfortable with this statement. If they have to change their position by the same amount, then they have to have the same accelerations too. Okay, so what do you do with this? Well, you make your free body diagrams. Here's a free body diagram for block 1. Here's a free body diagram for block 2. And here is a free body diagram for the pulley, which you may never have done before because it's pointless when the pulley isn't moving. However, once the pulleys start moving, it's going to be necessary. Okay, so what's the point of making free body diagrams? Well, writing Newton's second law for each object. In this case, here's the free body diagram for the pulley. The pulley isn't moving, so all it says is that the tension from the ceiling has to support 2 times the tension, so coming from below, okay? Ordinarily, you'd solve this system of equations, but I don't want to do a lot of that in this video. I'll do that at the end. Let's just look at setup, setup, setup. Okay, so now you're comfortable doing that. What happens now if the pulley moves? Okay, let's see what that looks like. The pulley has moved up, and now look at this. There's 2 gaps. There's a gap here, and there's a gap here. So we have 2 times delta x pulleys worth of gap to fill, and how do we fill it? Well, somehow these 2 guys are going to have to combine in order to fill that gap. One way to do it is they both move up by the same amount. So they've both moved up by delta x pulley plus delta x pulley equals 2 delta x pulley. That's one easy way to do it. But they don't have to do that. One can move a little bit more than the other. And notice this equation is still true. It's still true because this guy got a little shorter and this guy got a little longer. But it happened by the same amount based on what we talked about earlier. The implication of this is, of course, that A1 plus A2 equals 2 times the acceleration of the pulley. Okay, now I want to do this same thing in a completely different way. I want to label the actual positions instead of just talking about how the positions change. And the reason I want to do this is to talk about formal coordinate systems. This is a much easier way. You don't have to be as clever when you do it this way. You can just do the same thing over and over. And when you get into more advanced physics, being able to set up a formal coordinate system is really the skill you want to be good at. So what do we do with this? We're going to say the following: that the length of the string is equal to this distance plus this distance. That's something that seems so obvious it's not worth writing down, but by writing it down, we're actually able to do stuff with it. This is called a constraint. In other words, x1 and x2 are going to move based on the forces, but there is this thing that constrains their motion. So what do you do with this? You actually take a derivative on both sides. The derivative of the left side is 0 because the length of the string can't change. This side becomes 2 times the velocity of the pulley. So this is v pulley, this is v pulley. You get 2 of those, and you get a v1 and a v2. Take another derivative, and holy smokes, we get the exact same thing that we got last time when we were looking at changes. Okay, so what do you do with this? Well, as always, you make free body diagrams. Here's one for the block on the left. Here's one for the block on the right. And here's one for the pulley. In this case, the pulley is moving. Now, in here, I said that it had some acceleration upward. Well, what gives an acceleration upward? There must be some force. And this is a free body diagram, and you don't put accelerations on free body diagrams. So I just said, okay, there's some really big force, and it's pulling it up. The purpose of these free body diagrams is, again, to write Newton's second law for the block on the left, Newton's second law for the block on the right, Newton's second law for the pulley because the pulley is moving, and our constraint. If you look at this system, you will see that you have 1, 2, 3, 4 unknowns. 4 unknowns and 4 equations. You might say, hey, wait a minute, what about F? Well, I'd have to give you F or a pulley, so you got to choose between those 2. Okay? All right, great. If you're comfortable with that, let's get crazy. What happens if we have a system that looks like this? Already, this looks not fun. You've got 3 pulleys. You've got, gosh, I don't even, 1, 2. We're going to count the ropes as well. Okay, so the first thing we're going to do is set up a coordinate system. Okay, so I'm going to call this pulley x equals 0. I could have called it anywhere, but I choose that point to call x equals 0. The other thing to bear in mind is we've got 3 ropes, so I color-coded them. Rope 1, rope 2, rope 3. 3 different color ropes. Each of those ropes provides us with an opportunity to write a constraint. So what do those constraints look like? For the orange rope, it's this guy's position minus this guy's position, because remember, we're measuring all the way from over here. So that's that distance. That's equal to L1. The blue rope has this section plus this section plus this section. So I have 1, 2, 3 terms. That's equal to L2. And then the green rope has 2 sections. This section plus this section. Now this is a little funny here because I'm not subtracting for the green rope, I'm simply adding. And what we'll end up with later is a minus sign there. You'll see what that looks like. So here, if you differentiate twice like we did last time, you'll end up with this. If you differentiate twice, you'll end up with something like looks like this. And this is what I was saying earlier, that because I chose to add them here instead of subtract, I end up with a minus sign. But really all this is saying is that this block is moving downward while this block is moving, or we'll say while the pulley, for example, is moving to the right. So 1 is positive and 1 is negative. The takeaway from all this is if you get rid of the acceleration of b, then you end up with this relationship. So 3a1 equals minus 2a2. It's not quite as straightforward as it was before, but setting up these constraints is as straightforward as it was before. I just had more of them, and honestly, the algebra wasn't too bad. Just to show you that this is consistent with the other way of doing things. So think about it this way. If I move m2 up a distance x2, so I just pushed this pulley because if this guy moves up, I create this distance. Now think about this. This rope is connected to the pulley. If this pulley slides forward, it creates 2 delta x2. It creates delta x2 on either side, and someone has to pull that rope in order to make up for it. Who pulls it? M1. So if M1 has to move a distance delta x1, then think about this. M1 creates delta x1 here and delta x1 here. But M1 is also connected to a pulley, so it creates 2 more delta x1s there and there. That means that if I move M1, I create 1, 2, 3 delta x1s. If I move M2, I create 1, 2 delta x2s. So what do? I say 3 delta x1s has to be paid for with 2 delta x2s. And then, of course, if I differentiate, I end up with 3a1 and 2a2. That's a little confusing. So let me give you another example immediately where I do this sort of trick, right? So I say, all right, in this case, if M1 is connected to one rope and that one rope is connected to a pulley, then if I move M1, I create 1, 2 bits of rope. In this case, M1 is connected to one rope here, and then one rope that's connected to a pulley, so times 2, because I'll create here and here. That means I have 1, 3, 4. 4 A1s to 2 A2s. I'll show you another one. I have made it slightly more complicated in this case. It's starting to get a little bananas here, right? So in this case, M2 is connected to 2 ropes. Each of those ropes is connected to a movable pulley. So you have 1, 1, but each of those creates an additional 1 and 1. So I have really, from this rope, I have 2, and from this rope, I have 2. And so in front of A2, I put a 4. How about for M1? Well, for M1, I have this rope, which is connected to 2, so that's 2, and then I have 1 here and 1 here. So 1 plus 2 plus 1, 4. 4 and 4. You may say, okay, well, what if you add more blocks? Fine, no problem. Here's the idea. M3 is connected to one rope, okay? M1 is connected to one rope here and then one rope here, which is attached to a pulley, and so you create 2 here. So I have 1, 3, so I get a 3 in front of my 1. M3 is only connected to 1, so I put a 1 in front of this. And this guy is still connected to the 2 ropes, which in turn are connected to 2 more. So this guy gets 2 and 2 again, so 4. Okay? If you find this confusing, I don't blame you. I'm sort of showing that this is quite a clever way to do it, but you have to, it can get a little confusing. And that's why really what I'm trying to sell in this video is let's just make some constraints. Let's make some constraints. I have 4 ropes and 3 blocks. Here's rope 1, here's rope 2, here's rope 3, here's rope 4. This takes up a little bit more space to write, but there's less thinking involved, and in general, you want to think less in physics. Maybe your physics teacher will tell you different, but I say the less thinking you do, the better. If you have someone who's already developed a system and it works and it always works, and this always works, you can just continue to use it over and over again. So I've set these up. I've just gone through the blue rope, the green rope, the purple rope. And if I do a little teensy bit of algebra, I end up with an equation that looks like this, which of course is the same thing I ended up with over here. I've noticed that as I've taught this, some people like it better one way and some people like it better the other way. You do you. You do you. You do the way that looks the best. I will tell you that making formal coordinate systems is something that is useful beyond these sorts of problems. And this sort of trick is very fast if you like it and you understand it. It's very fast for these kinds of problems, but it's not really useful for other kinds of problems. Okay, all right, as promised, I will do a real problem, the Double Atwood. This normally has like 3 stars next to it in most introductory physics textbooks. But if you understand what we've talked about in this video, it's really not a thing. So the first thing we'll do is we'll come up with position labels for everything. We will acknowledge that we have 2 ropes. We will write constraint equations for each rope. So I have 2 sections of green rope, 1, 2, 2 sections of purple rope, 1, 2. I will differentiate those in order to get my accelerations. I will combine those. That is my constraint equation. What else do you do? Well, we make free body diagrams. Free body diagram for M1, free body diagram for M3, free body diagram for M2, and a free body diagram for the movable pulley. Notice I have 2 tensions. There's a T2 and a T1. That's because they are separate ropes. Okay. Notice that the pulley has 1, 2 tensions pulling down on it and 1 of the green tensions pulling up on it. What is the purpose of making free body diagrams? Well, of course, it's to explain to us how to write Newton's second law. So I have 1, 2, 3, 4, 5 equations and 5 unknowns. 1, 2, 3, 4, 5. There you go. One thing that you'll note is I said that the mass of the pulley times the acceleration of the pulley is 0. I don't say that because the acceleration of the pulley is 0. I say it because normally in these kinds of problems, you take the acceleration of the pulley to be 0. I'm sorry, you take the mass of the pulley to be 0. If you don't want the mass of the pulley to be 0, don't take it to be 0. But I'll just say normally these are massless pulleys. And so that creates an easier equation there. And then, of course, at the very bottom, this is our equation of constraint. As far as physics goes, this problem is done. All that's left to do is a mountain of algebra. So here I've gone and I've worked out A3. I do not recommend you do the algebra this way. I put it there just so you could see that this is only solving for one thing and it's a lot. The thing is, we want to know how to do algebra. We certainly don't want to waste our time doing it. It's not good work for humans. It's good work for computers. So how do you do the algebra for this problem? You open up a Jupyter Lab notebook, you copy the code I have, you change your equations to whatever equations you have, and then Python will say, yum, 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 thanks very much. I love algebra, and you can spend your time doing something better. If you don't like Python, use your favorite symbolic math program. The nice thing about this is that it's free, and if you take the 10 minutes to learn how to write these sorts of statements, you can do all your algebra for free for the rest of your life. Okay, hopefully this video was more helpful than confusing.